I've been asked to do some limit problems, so we'll do a rapid fire 5, which might turn into 10 because they don't take long to do. So let's look at the limit as x goes to infinity of 16 times 1/2 to the x plus 3. And I want to know what happens as I go from 0, 1, 2, 3, 4, 5, 6, 7. I keep doing that forever. Do I get knowledge over here as to, am I going to Montreal? No, it's usually a number, right? Always a number. All right, so let's just take some analysis here. I mean, if you know how to graph this, you already got your answer. So 1/2 to the 0 is 1, so I get 16 plus 3. 1/2 to the 1, half of 16 is 8 plus 3. Half of that is 4 plus 3. I think we already see a trend here. 2 plus 3, 1 plus 3, 1/2 plus 3, 1/4 plus 3. I think I'm going to 3. All I did was use numbers. I got bigger and bigger and bigger numbers because I was told to go to infinity, which is all about the x side of the table. And putting the numbers in is all about the y side of the table. And as numbers got bigger, I'm getting closer and closer to 3. And if we graph this, I hope you see exponential decay. I hope you've done enough work at this stage of the term that's working knowledge. And what you do is you follow the x-axis. With one hand, my x-axis values are getting bigger. And for each x value, I'm getting that. So if I pick this x value, I'm getting that altitude. And those altitudes are converging at a y value of 3. Another problem. How about we do the limit as x goes to 7 of 3 over x minus 7. I guess I like the number 3. Well, if you know what the graph looks like, you already know your answer does not exist. Then let's look at y. Well, the issue here is I could come from 7 from the below. If there was a negative sign, then I'm coming in from 0, 1, 2, 3, 4, 5, 6, 6.5, 6, 6.9, 6.99999. And if I'm coming in from the other direction, I'm coming from 10.98, 7.5, 7.7, 7.01. So why don't we cut to the chase? And let's look at those two. 7, I don't care about. 6.99, I do. 7.01, I do. If I put 6.99 in here, I get 3 over negative 0.01. That's minus 330. So 1/10 is 30, so 300. So that's minus 300. Tired man here. So this is a negative sizable number, right? That's a sizable number. So this is minus 1 over 100. I had to do that with my brain right now to see the minus 300. Whereas if I do 7.01, I get 3 divided by positive 0.01, which is positive 300. If they're not the same, then it doesn't have to be absolutely equal, but one's headed towards negative infinity, the other's headed to positive infinity. It does not exist. If I had, that's the question I was asking. If the plus sign was there, then I'd say, oh, from the positive side, looks like I'm going to positive infinity, because I could always throw another 0 in here. If I put another 0 in here, I get another 0 there. I could do that forever. Yep, I'm not going to do it forever. If the minus sign was there, well, now we're looking at this part of the table here. And again, every time I put a 9, I get another 0, and I could do that forever as well. But that's headed to negative infinity. That would be the answer to that. And if I don't put a plus or a minus, then we have to look at both situations. And if they don't converge, we say does not exist. Now, the ones that you'll see at the next level the most early on, and it also coincides with our graphing of rational functions. So if I said f of x, I'll leave that up there. That way I can write the limit of f of x and have less erasing to do. Let's say we had x minus 2. Let's go 4x minus 2 over 3x plus 1. What happens in this situation if we go to infinity? Well, again, maybe graphical is important. So let's say that we have y equals x. I think this is the best way to explain it. I think I need more space. Yes. So let's just start with y equals x. All right. So this is really, every altitude is going to be 3 times the size. So whatever that altitude is, let's make it smaller here so I don't have so much drawing to do. Let's do 3x over 2, all right? So if this is y equals x, and I tried to, should be more of a 45-degree angle, but for our purposes, it's helpful. So in the numerator, I have a line that's going to be 3 times this size. So there's 1, there's 2, there's 3. So I have a line that goes through there. And in the denominator, I've got one that is just twice the size of y equals x. So, and so now I want to look as I go out here to infinity. What's going on? Well, let's get rid of y equals x now. Let's see. Well, that's 2 and that's 3. And it looks like the same ratio to me. Whatever this is, it's in a 3-to-2 ratio. Maybe that's 30, maybe that's 20. Maybe that's 300. Maybe that's 200. Sure looks like 300 in the numerator with a little bit of something. 200 in the numerator with a little bit of change. I think I have a 3-to-2 ratio. I mean, when I put a billion in here, losing $2 on the sidewalk's not going to break me. Now, what happens if it was square? It was square. All right, so let's go back and look here. I'm going to have to draw a little funky drawing here. So there's my squaring process. There's my altitude. Let's see, 3x squared, it's going to be 3 times that size. 1, 2, 3, whereas 2x squared is going to be twice. Let's see, that's a 2-to-3 ratio. Let's get rid of this now. So that's, you know, a 2, and that's a 3. I come over here, that's a 2. Let's make it a 20. Oh, let's make it a 30. Let's make it a 200. Let's make it a 300. I think you're getting the idea, I hope, that if the biggest power, which dictates end behavior, is the same, then it's the ratio of the coefficients, and that's why. Now, you could have put 100 in here. 100 squared, it's got 4 zeros. And we're subtracting 2. And this one has 4 zeros as well, and we're adding 1. I hope you can get a feel for that 3-to-2 ratio. All right, now, what happened if this was a 3? Let's make this one a 2. Make a new problem. Got too many things there, it's hard to see. So I should be putting my answers here. Let's say we have 2x plus 1 over 2x squared plus 1. All right. Well, 2x plus 1, you know, is a doubling function, linear. So let's just put it through the origin. I know it's not, but if you're looking at infinity, you can't see small numbers anyway. So big picture, 2x squared. Boom. Well, I'm looking at this amount, and I'll do it sideways. Let's just say that's that amount. And that this amount, God, I got to stand up, you know. Oh, Lord, is, whoa. How many times does that fit into that? Doesn't. So anytime the denominator is bigger than the numerator, goes to 0. Those are just rules. So let's look at a more difficult one. Let's look at x squared plus x minus 6 over x squared minus 9. And what happens as we move towards, let's call it f of x. Let's see if we go towards -3. Well, you want to definitely factor this thing. So x squared minus 9 is x plus 3x minus 3. X minus 3. And I can see now when I put minus 3 in, I've got an undefined fraction. No problem, because I don't care what happens at 3 anyway. It's in the table as I approach 3 from below and from above. Do those numbers converge? They don't have to be exactly equal. I mean, if I had a table and 3 is undefined, but here I have 2, 0, 0, 5, 7, and over here I've got 2, 9, 0, 3, 2, I would probably say it's going to positive infinity. All right, because you can see numbers smaller, smaller, going bigger, smaller, smaller, going bigger, which means every time I add a 9, it's probably going to get bigger. Every time I add a 0, it's probably going to get bigger. Looks like they're going to infinity. But what's going on in this situation? Because that's the one we're looking at. All right, so I got to get a table. Or maybe I haven't finished this yet. So plus x, so that's an x plus 3 over multiplied times x minus 2. Oh, well, you know what? That's gone. All the crazy behavior goes with it. Can I put -3 in there right now? Yeah, I can. So I know exactly where it's going. It's going to -5 over -6. It's going to 5 over 6. That's my answer. So what did the graph look like? Because I can't really use -3. Well, this is what we're just starting to practice. Asymptote, x equals 3. That's where we're going to get small numbers. If I put numbers like 3.01 in there, I'm going to get 0.01, which is going to go into 1 lots of times. X minus 2, so 2, 0. -2, -3, 2/3. It doesn't hurt to watch me do this. End behavior. Let's do f of x right now. This is where we use it. Where's that function going? Where's that function going? It's going to 1. We practiced that. They're the same exponent. There you go again. So that's very helpful for the graph. I wrote x equal, I meant to write y. Y equals 1. Okay, so I can see my graph now. Looks pretty simple. Boom. Boom. So now that we have a graph in front of us, let's go back to 3. We're looking at, this is f of x. Another way of saying y. And this is the x-axis. And so as x goes to 3, what's my answer? Well, you're going to negative infinity when you put numbers in like 2.999. You get positive infinity at 3.001. So as I said before, it does not. Oh, I asked a different question, didn't I? So this does not exist. I think what we started with was -3, right? Yeah, that's what we started with. Yeah, we started with negative. That was the original question. We said that was 5, 6. Why? Because we don't care about these fractions, these factors anymore. They're gone. And there's no reason I can't put -3 in. And however, if I wanted to present the graph to you, then I would have to make a point here that doesn't exist. Because -3, we still have to think about the domain restriction. I'm not allowed to use it. I did use it. I almost forgot to put the point of discontinuity. And that coordinate is -3, and we found out what that coordinate is. That's where I'm headed. I'm headed to 5, 6. And let's see, how could I show that? Let's do -3. No, I don't think I can. I've lost myself in these 3s, so I'm gonna get out of this problem and just do another one. I think I did it right. Could have made a careless error in what I was saying there, but the conversation was the correct conversation. So let's look at the limit as x goes to infinity of 5x to the 7th minus 6x squared plus 2x minus 9 over 3x to the 7th plus 5x to the 5th minus 4x cubed. That's good enough. Where am I going if I go to infinity? Go ahead and do the problem. I'm going to 5/3. Why? Because we established that when the big players have the same exponent, it goes to the ratio of the coefficients. Let's try another one. What's the limit? As x goes to infinity of x to the 10th over 2 to the x. Pause, go ahead, do it. All right, this is going to 0. Why? Exponential growth always overtakes polynomial behavior. Now, how can I show this? How about we do let x equal 20? That probably is enough. So 20 to the 10th, 20 times 20 times 20 times 24, 5, 6, 7, 8, 9, 10, all of that's multiplication. 2 to the 20th, maybe this isn't the best. 2 to the 20th, so I got 2 times 2 times 2 times 2. 16 times 2, well, there's 32. Okay, and I'm going to do that 20 times. Right now I've done it 5, so I got to do it 4 times. See, let's make this go, let's let x go to 100. Let's let x go to 100. So I would have 20, I would do 100 to the 10th. So each of these would be 100. All right, so pretend they're all 100. Let me just get started here. 100, 100, 100, 100, 100, 100. I think this will explain it better. And those are all hundreds. All right, so let's do 2 to the 100th. So that's 1, 2, 3, 4, 5, 6, 7. I am already bigger than this number, and I'm doing it 10 times. 1, 2, 3, 4, 5, 6, 7. 7 goes into 100 more than 13 times. Okay, so you can see that this is already overtaken that calculation. So picture doing it 1,000,000 times. All right, there'd be 1,000,000 of those. And how long does it take to get to 1,000,000? Let's see, 2 to the 6th to the 64, right? 16, 32, 64, 2 to the 64. So 6 is 64, so 7 is 128. So 8 is 256. So 9 is 512. So 10 times. If I do 2 to the 10, I'm already at 100. If I do 100, I'm getting lost in the size of infinity. Needless to say, it's going to take, I'm going to get a number here that is going to be astronomically bigger than that one. All right, late in the day, get a little tired, but that overtakes that. I don't know what I could put in there and show it because it takes too long to write it out. Go to a calculator, do 2 to the 100th, do 100 to the 10th. Okay, and then if that doesn't clearly show you, make it 1,000, make it 1,000. That doesn't show you 10,000, 10,000. You're eventually going to see the exponential get much bigger. And if I have a number here like 7, and this number in the denominator keeps getting bigger and bigger and bigger comparatively, I'll throw 2 zeros for every one. 2 zeros for every one. I hope you can get a feeling for that quantity. So I guess that's, let's see, I got one more here. So what's the limit as x goes to infinity of 5x minus 2 over 3x squared plus 7x minus 4? And I hope, pause, okay, 0. Why? The exponent in the denominator is bigger than the one in the numerator, which means it's just like the previous problem. The denominator is getting faster than, they're both going to infinity, but this function is going up at a rate significantly different than the linear one. So eventually, this denominator is getting, the y value on that denominator is getting so much bigger than the numerator, the quantity in the numerator for the same x value. Okay, maybe I can show it with a number. 100 squared is going to be 4 zeros. 100 times 5 is 2 zeros. 2 zeros, 2 zeros. I already got 5 over 300, which is 1 over 60, and that's getting close to 0. And so just a simple number there was helpful. All right, so limits are about their y values. They're on the y side of the table. And as we approach an x value, can we see if there's convergence? That's what we're starting to talk about. And I'd rather have you do it now because in calculus, kids didn't talk about it at all and took a couple of months because it's, you know, it's not as important as differentiation and integration, although it's what dictates the ability to do those concepts, to do those techniques. So it's, calculus is based on limits. So I kind of take it back. It's really important to get a sense of limits, but you can't spend an entire semester on them. So I want you to start thinking about them now. All right, ciao.